Hello, I am Manavjyoti Choudhury, Assistant Professor in the Department of Computer Science and Engineering of Assam Downtown University. In this video, I will talk about the FCFS or First Come, First Serve CPU scheduling algorithm. CPU scheduling is the basis of multi-programmed operating systems. By switching the CPU among processes, the operating system can make the computer more productive. The idea of multiprogramming is very simple. A process is executed until it must wait, typically for the completion of some input-output request. In a simple computer system, the CPU would just sit idle. All this waiting time is wasted and no useful work is accomplished. With multiprogramming, however, we try to use this time productively. Several processes are kept in memory at one time, and when one process has to wait, the operating system takes the CPU away from that process and gives the CPU to another process. This pattern continues, and every time one process has to wait, another process may take over the use of the CPU. Scheduling is a fundamental operating system function. Almost all computer resources are scheduled before use. The CPU is, of course, one of the primary computer resources. Thus, its scheduling is central to operating system design. Before discussing scheduling algorithms, let us get familiar with two terms that are associated with scheduling. The first one is waiting time. The CPU scheduling algorithm does not affect the amount of time during which a process executes or performs some input-output operation. It only affects the amount of time that a process spends waiting in the ready queue. Waiting time is the sum of the periods spent waiting in the ready queue. Another term associated with CPU scheduling is turnaround time. From the point of view of a particular process, the important criterion is how long it takes to execute that process. The interval from the time of submission of a process to the time of completion is the turnaround time. Turnaround time is the sum of the periods spent waiting to get into memory, waiting in the ready queue, executing on the CPU, and doing some input-output. It is desirable to maximize CPU utilization and throughput and to minimize turnaround time, waiting time, and response time. CPU scheduling deals with the problem of deciding which of the processes in the ready queue is to be allocated the CPU. There are many different CPU scheduling algorithms. The simplest CPU scheduling algorithm is FCFS or First Come, First Serve CPU scheduling algorithm. With this scheme, the process that requests the CPU first is allocated the CPU first. The implementation of the FCFS policy is easily managed with a first in first out or FIFO queue. When a process enters the ready queue, its process control block or PCB is linked onto the tail of the queue. When the CPU is free, it is allocated to the process at the head of the queue. The running process is then removed from the queue. The code for FCFS scheduling is simple to write and understand. The average waiting time under the FCFS policy, however, is often quite long. Let us consider an example of three processes, namely process P1, P2, and P3, and their burst times in milliseconds as 24 milliseconds for process P1, 3 milliseconds for process P2, and 3 milliseconds for process P3. These processes arrive at time 0 into memory. If these three processes arrive in the order P1, P2, and P3 and are served in FCFS order, first of all, we draw the Gantt chart for them. And from this Gantt chart, we find out their individual waiting times, and finally the average waiting time for the processes. So from the Gantt chart, we find out that the waiting time for process P1 is 0, for process P2 it's 24, and for process P3 the waiting time is 27. So the average waiting time for these three processes is 0 plus 24 plus 27 divided by 3, and that is equal to 17 milliseconds. If these processes arrive in the order P2, P3, P1, however, the result of their average waiting time will be different. First of all, we draw the Gantt chart and find out that the waiting time for process P1 is 6, this time 6. For process P2 it's 0, and for process P3 the waiting time is 3 milliseconds, and thus we find out that their average waiting time is 6 plus 0 plus 3 divided by 3 equal to 3 milliseconds. This reduction in average waiting time is quite substantial. Thus, the average waiting time under a FCFS policy is generally not minimal and may vary substantially if the process CPU burst times vary greatly. In addition, consider the performance of FCFS scheduling. In a dynamic situation, assume we have one CPU-bound process and many I/O-bound processes. As the processes flow around the system, the following scenario may result. The CPU-bound process will get the CPU and hold it. During this time, all the other processes will finish their input-output and move into the ready queue, waiting for the CPU. While the processes wait in the ready queue, the I/O devices are idle. Eventually, the CPU-bound process finishes its CPU burst and moves to an input-output device. All the I/O-bound processes, which have very short CPU bursts, execute quickly and move back to the I/O queues. At this point, the CPU sits idle. The CPU-bound processes will then move back to the ready queue and be allocated the CPU. Again, all the I/O processes end up waiting in the ready queue until the CPU-bound process is done. There is a convoy effect, as all the other processes wait for the one big process to get off the CPU. This effect results in lower CPU and device utilization than might be possible if the shorter processes were allowed to go first. The FCFS scheduling algorithm is non-preemptive. Once the CPU has been allocated to a process, that process keeps the CPU until it releases the CPU, either by terminating or by requesting some input-output. The FCFS algorithm is particularly troublesome for time-sharing systems, where it is important that each user get a share of the CPU at regular intervals. It would be disastrous to allow one process to keep the CPU for an extended period. Thank you.